Okay, today we are going to start to debate about the filter design in digital signal processing. Okay, so we have title in here, digital signal processing, and so our topic is that filter design, but in what? In discrete domain. Okay, first of all, the filter design is or the has an utmost importance to get the better results in real-time applications, because in the real time we have the many disturbances such as the noise or unwanted signals or the something like that. Okay, due to the remaining noise and these signals from the main body, we need to spread the whole the things by using the what? Discrete filters. Okay, in order to design the discrete filter, first we need to design the analog continuous filter, which means that we can utilize the what? The analog filter design to create the what? The discrete one. Okay, by using the some methods, for example the bilinear transform. Okay, this is important because in the real life application the analog filter always will with the RC or op-amp, operational amplifier designs, but these filters can be manipulated with what? Mathematical formulations. Which is the easiest way to what? To build your filter, because you can program the digital filters, discrete filters, by using the anyway. But if you want to design the analog filter, this is the most efficient way to what? To suppress the whole signal in the continuous time domain. But we should design this filter electronically, and then we have the many cost if we don't have any information about the filters or the noises. Okay, but in the discrete filter we can optimize the R design by using the what? The bilinear transform in here. Okay, in the literature we have the what? The two kind of important filters. There are many filters, but we have the two special filters in order to build our algorithms. Okay, the special filters can be given by this one. First of all, we have the Butterworth filters, which is continuous time domain filter. Guys, just remember that. And also we have the Chebyshev filter. This is standard implementation of the filters, but in what? In analog domain. Okay, and so the Butterworth filter contains the pole design, just like the what? If we have the S-plane, just like the Fourier transform or the Laplace transform, and then we can set the whole the poles to the desired points, which means that we can define what are cutoff frequencies in here. Okay, and so everything which is given in the what? In the S-plane or the frequency domains. Okay, and so this Butterworth filter creates the maximal flat response at each frequency input in here. And also we should use the few parameters to what? To create the R designs. Okay, to design it. But what's the meaning of the maximal flat response and the few parameters in here, just like this one? First of all, we know that we have the Bode plots in here, just like this one. This is the frequency in here, and also we can set the cutoff frequency, which means that this cutoff frequency is to be used to what? To select the which frequency is our region, is our boundary to what? To pass or stop the signals. For example, if we have this signal in the dB domain, the energy domain, we can set the 0 dB in here. This is what? This is in the magnitude form, which equals to what? Equals to the 1, okay? But if we use this filter, and so this is the what? This is the 1 point in the magnitude form, and so we can set the R signal at the minus 3 dB, which is the half of the power of the R signals, and so this cutoff frequency can be set in here, okay? And so before the FC happen, or the, for example, if there is any signal is lower than the FC, this signals is passed, but the other signals is not in here, okay? And also we have the Chebyshev filters, okay? These Chebyshev filters, just like the what, the pole design in the what, in the S-plane, okay? And so this S-plane creates do not the what, the maximal flat response, but the equiripples in passband regions and fastest decrease in what? In stop band. But in order to design these things, the many parameters should be utilized, okay? What's the difference between the Chebyshev and the Butterworth in here? In the Butterworth filter, we have also a Bode plot in here, just like this one, the FC, and also we have the dB, the signal energy form, or the power form in here, okay? And so we can create the what, the 0 dB region in here, just like this one, okay? But the Chebyshev filter creates the what, this kind of outputs, okay? Which means that we have the what, the minus 3 dB values in here, and so this filter to what, to pass these locations, but not this one, okay? But the difference is given in the what, in the fastest transient response, transition response in here. We have the fastest decrease in here, and so if we suppress the whole signal after the FC, and so we can use the Chebyshev filter. But if we want to create the more robust and flat response before the FC, and so we can utilize what, the Butterworth filter. But the common point is that we can design the R specific filter using the what? Using the G, the energy form frequency curve. And so if we want to design any filter, we can use this graph in order to what? In order to design or build the R filter specifications in here. For example, the cutoff frequency. For example, stop band frequency, passband frequency, or passband ripple, or the stop band ripple, okay? And so if we condition this Bode plots or this G or magnitude F graph, and so we can design to what? To design filter, we can set the transfer function, or in another case, the R filter to the what? To the specific parameters, okay? This is the most known digital filters in the analog and discrete domain, guys, okay? So this is the reminder one. Reminder one. And also we have the reminder 2. Bode frequency. So in order to get the what, in order to get the frequency range. What's the meaning of this? If we have the any fs input to the watt to do any system in here gs, we have the cs signal, or this is the us. And so if you want to pass the some frequency and the others not, we can design this gs value based on the what the body frequencies in here. And so in this body frequency, s, or the s-plane variable in the Laplace domain, should be assigned with what the j dot w. This is the angular frequency of the r notation, 2 pi f. Okay, and so if we want to design this curve, and then we can build this frequency plots in here. And so we need to give the what reminder tree in here, just like this one. And so we need to calculate what the body magnitude and phase, right? Because if we have any frequency signals in here to be applied to the GS, some of the signals is amplified, but some of them not, or some of them passed, or some of them stopped. Okay, and so we need to design this GS to what, to create the FC, or the cutoff frequencies based on the what, based on the body plot in terms of the what, the magnitude and the phase with respect to the frequency region. Okay, and so in the reminder tree, just remember that the magnitude or power of the signal is given by, for the following formula. The magnitude can be built with the what, the 20 dot log basis 10. And so we have the what, the HGV in here, just like this one. This is the R system, and the phase can be given with the what, with these terms, HGW, tangential components of the what, the imag, or imaginary units of the what, the HGV, and real part of the HGV. Okay, GW. And so this is the representation of the Euler identity. And so this is the magnitude of the R signal, but in the what, in the decibel formations. Okay, these are the basis for the what, for these characteristics. But how we can calculate these informations? The examples can be given. Consider that we have Hs just like 1 divided by s plus 1, and so calculate the magnitude and the phase. This is our problem. Okay, and the solution can be given or written with the what, with these steps. First of all, we should assign the s j dot w. Okay, and so if we have this information, hjw is rewritten as the jw plus 1, and so in the complex conjugate form we have the what, we need to multiply with the what, the minus jw plus 1, and so we have the 1 minus jw divided by 1 plus w square. Okay, and so in the real and the imaginary part, we can write that the real part of the R filter is the 1 divided by 1 plus w square, and so the imaginary part is minus w divided by 1 plus w square. Okay, and so our magnitude can be combined with this information, or we can take the what, the absolute values of the real and imaginary part to find out what the Pythagorean hypotenuse. Okay, and so if we have this information, HGV, GW, absolute values can be given by with what, the 1 divided by 1 plus omega square and plus 1 w 1 plus w square. And so if we have these nominations in here just like this one, and then we can take the 1 divided by square root of the 1 plus w square. Okay, these are the nominations in the in our algorithms. Okay, because the square form is given in here, and then we can take the hold values based on these informations in here just like this one, but we need to add the square form in here. Okay, and so how we can calculate the fuzz of the R algorithm. This is the this is the magnitude of these terms, and also the fuzz can be written as the hjw, which is equal to the tangential or arctank minus w 1 plus w square divided by 1 plus w square, and so tangent inverse value or the arctan minus w can be given for the for the fuzz diagrams. Okay, these are the basis for the for the calculations of these terms. Okay, this is a reminder section to analyze your system in the frequency domain, which we can replace the s with the j dot w in the other identity formulations, and then we can create our magnitude form in terms of the real and imaginary part, and then we can find out our radius on the Euler identity formulations. And so this radius can be represented with the with the magnitude values, but the fuzz is given by with the tangential components of these terms. Okay, so this magnitude and fuzz representation of the R filters. But in the next case, we need to talk about the body plot, and it is representation or the drawing fuzz in the in the algorithms. Okay, and so for a filter, we need to analyze it in body plot, because every case or every process should be included this body plot, because the body plot is true, and so the R filter is true as well. Okay, in terms of the magnitude and F curve in here, and so which is given by this one. And so we can draw the R curve in here just like this one. Okay, and so this is generally assigned with the magnitude or the dB form in here. If we have the magnitude form, and then we have the one-to-one process in here, or 0 dB formulations, because in the previous case we give these nominations in here just like this one. If the HGW, the absolute form of these things, is equals to the 1, and so this energy form is to 0 decibel. Okay, and so also we have the 0 values in here at the magnitude. Okay, and so this is the minus infinity dB, right? Minus infinity, and so there is no power to be transmitted to the to the output one. Okay, and so the ideal filter should be given by with the with the FC value in here, and so we can draw the ideal filter just like this rectangular form. If we have the ideal filter just like this one, and so before the cutoff frequency we have the 1 value in here, but after the upper values of the FC should be equals to the 0. But this is the ideal filter. Okay, we don't have any ideal filter in the real-time applications or in continuous domain, guys. Okay, but we can design another parameters in here just like this one. First of all, if you have any signal in here, And then we can build these nominations in here, just like this one. And so maybe we can design the our real filter just like this one. This is the real filter design. It looks like it, okay? Because we don't have any ideal signal, but we must learn that these values must be equal to the 3 dB value in here, okay? This is important. So in this case, we define the new parameters in here. The region between these two things is called the passband ripple. And so this region that we call to the stop band ripple. This is a ripple or the fluctuations at the magnitude and the power form of this filter design, okay? And so also we can draw these terms in here just like this one. So this is a fastest decrease in here, and so this is called the transition white. In terms of the frequency region, for example, the FC is equals to the 300 Hertz, and so we may create the 200 to 400 transition white for a given application that we need to build it, okay? And so these are the critical parameters in here, just like this one. And so if we manipulate the R system or the R design of filter in the S domain, in the frequency domain, and then we can build these characteristics based on the frequency values and the magnitude and the dB form. Generally, in the literature, we have the normalization values of these terms in the frequency range. For example, this one is equals to the Fs sampling rate divided by 2, and in terms of the pi radian divided by sample. This is the frequency range of these terms, okay? And so this is called the normalized frequency. For example, if you have this normalized frequency, and then if you sampled your signals at the rate of the 1000 Hertz, and then you can assign to this one the 500 Hertz, and so you may choose the cutoff frequency based on these terms. And so the sampling rate is another important parameter to design your system. For example, if you utilize the 10,000 sampling rate, and so you may choose the different parameters for for your filter design, for the same cutoff frequency, passband ripple, and the stop band ripple, guys. Okay? These parameters are the essentials to establish the filter design, but some of the concepts should be revised in in the body plot to build the R parameters. For example, we need to explain the cutoff frequency, passband ripple, transition white, or stop band ripple in here. Okay? And so we need to add another reminder in here. Okay, first of all, the number of reminders is that the reminder 1 is body function. Okay, the body plot can be drawn based on transfer function, guys, which is given in the S plane, just like this one. We have always the HS in here, and we have the numerator and the denominator. Okay, for example, from the previous example, HS is equals to 1 divided by S plus 1. Okay, this is the reminder 1 for the section 1. Okay, and also we need to continue these terms in here, the remainder 2 cutoff frequency. This is a break frequency to what to our applications. Okay, it is defined as as at which the magnitude of TF decreases to 1 divided by square root of 2, or in another term 0.070. Okay, or in energy or the power notation minus 3 decibel point, which is to what? The half of the power. Okay, and so in order to do that, we need to use these two concepts to what? To design, for example, the low pass filter based on these informations. Okay, and so as always we do, we need to create the examples. Design a low pass filter for example, the HS can be built with what? 1 divided by RCS plus 1. This is equals to what? The R and C. This is the first order low pass filter at the what? At the V out. Okay, but we need to determine to the what? To the R and C value for a given the cutoff frequencies. Okay, and so we need to create a stage for these terms. Firstly, we need to write to what? The S is equals to the JW, and then HJW must be equals to the what? The 1 divided by RCJW plus 1. Okay? These are the what? These are the frequency representation of the R transfer functions. Okay? And so we need to calculate what the magnitude of these signals. HJW, this is the hypotenuse of the Euler identity formulation. This is absolute form, and so 1 divided by RCJW square plus 1. Okay, this is the magnitude. It's R basis. How we can do that? We need to multiply with the complex conjugate formulations in here, and so we have the minus RCJW plus 1, and then minus RCJW, right? This is the R term in here, and so we can take the what? These terms in here, RCW, but in the what? In the minus form in here, they are all the square form, minus plus 1. Okay, this is the multiplication of these terms, but minus terms removes to this one. Okay, and so after that the real part and the imaginary part should be squared in here and divided by with the what? With these terms. Okay. So at the third case, we need to set the parameters of these terms. And so, in order to find out the cutoff frequency, we need to take this HJW, which is equal to 1 divided by square root 2. Okay, and so 1 divided by square RCW square plus 1, which is equals to what? 1 divided by square root 2. Okay, coming from this equation, 2 must be equals to what? The RCW square plus 1, or in another terms, 1 must be equals to the what? RCW square. Okay, and so we can say that the WC is equals to what? The 1 divided by R and C. And also we need to convert these terms, convert frequency like this, the angular frequency. Just remember that angular frequency. And so the FC WC divided by pi 2, and so which is equals to 1 divided by 2 pi r and c. Okay, and so we can set any points in here by using what, selecting the new r and c values to what, to desired characteristics frequency form in here. Okay, we can design it in a simple way. For example, if we choose the what, this is the 1 divided by 2 dot pi, and so we can say the what, the c is equals to the 2, and then we have the 0.5 hertz cutoff frequency in here. Okay, this is just simple is that. And so in the next session we will drive the second order cutoff frequency representation in the what, in the underdamped natural frequency of the second order representation of the R transfer function. Okay.